Okay, so we're going to go ahead and start on chapter 2. Chapter 2 is going to be all about chemistry. And so hopefully this is mostly a review for many of you. I'm going to kind of go through this quickly. If for some reason you haven't had BIO201 or chemistry more recently, then what you can do is go ahead and watch my longer videos that are in the 16-week. You'll see I post the fast track videos, and then I post the longer videos that I usually post for my 16-week below that. But if again, this is just a review for you, you just had 181, then watch these fast track videos. As always, if you have questions and like I went through this way too fast for you, we can always set up some time and then I can go over this with you one-on-one, or I can set up like a review session or something like that. So just let me know. I'm here to help. So I'm going to go ahead and close my video because I know my video is a little bit delayed, and so that can be a little annoying for some of you. So I'm going to go ahead and get right into chemistry. Now, please don't dismiss this lecture. This is an important lecture because it's going to provide the basis for all of these chemical reactions that are going to happen inside the human body. So when we get into all the physiology and all these physiological reactions, things like digestion and contraction of the heart and things like that, the nervous system is going to be a big one. You're going to need to understand these fundamentals of chemistry. So again, understanding ion imbalances and electrical charges and how that's important in terms of like nerve conduction and things like that is going to be really important. So please take some time with this lecture. Don't completely dismiss it and go, we're in a biology class, chemistry is not important. That's not true, because all of the chemical reactions that happen in your body, I mean, your body itself is composed, right, of chemicals. And so all of these body activities that happen inside the human body are chemical in nature. And so it's really important for you to become familiar with the language and kind of the fundamentals of chemistry so that you can understand those physiological processes. Okay, so now let's jump into just some real basic chemistry. One, matter is anything that has mass and occupies space. You probably already know that. So again, it's always hard to picture that air is matter, but it is because it has mass. We can actually compress it. And we know it occupies space because we know we can compress gases so that they can take up less space. And then also, we know that it has mass because there are all kinds of chemicals. There's, oxygen molecules, there's carbon dioxide molecules, there are nitrogen molecules in our air. And so we know that those chemicals have mass, okay? So again, matter is anything that has mass, occupies space. Now, when we talk about weight, weight is just your mass plus the effects of gravity. So obviously on Earth here, when we're measuring mass, we have to take into account the effects of gravity. So the difference again between looking at your mass, on Earth versus the moon isn't really going to be something that we're going to have to deal with. So we're mainly, again, going to be measuring mass on Earth, which is going to be weight, okay? But just for those of you that needed the difference. So here would be like if your weight or mass was, 100 pounds on Earth, then, it might be only 16.6 on the moon. So again, difference in what, again, mass and weight are. So, but like I said, this won't be a big deal for us because we're primarily going to be dealing with stuff on Earth. So as you well know, matter exists in 3 states: solid, liquid, gas. Again, I'm not going to give you definitions because I'm pretty sure most of you are pretty familiar with those differences. Energy is just simply the capacity to do work or put matter into motion. And again, energy doesn't have mass, nor does it take up space. And the greater the work that's done, the more energy it's going to use up. So again, we're going to primarily kind of talk about energy in terms of the energy conversion. So we're going to talk about converting energy from like a potential stored energy in the form of chemical bonds as we break down those chemical bonds in our foods, release that energy, and then use that energy for kinetic energy, our energy of motion, to be able to, again, do all of these physiological activities that we need to do. So that's primarily how we're going to be talking about energy. So kinetic energy, again, is your energy of action, and your potential energy is your stored energy. So, and just like we talked about, energy can be transformed from potential to kinetic energy, and that's where we're really going to be. We're going to really be down here focusing on this. How do we take that stored energy? How can that stored energy be released? And then how can it be put to work for us? Okay. This is just a quick video, but again, I'm not going to play it for you. You can play it from the PowerPoint, but I'm not going to play it for you because most of you probably know the difference. So the difference between chemical energy and, potential energy and kinetic energy. So now we're going to talk about these different forms of energy that we're going to see specifically in the human body, and we will deal with all these forms of energy. So you should be familiar with these different forms of energy. One is chemical energy. This is simply the energy that is stored in the chemical bonds, such as the energy that's stored in the chemical bonds of the carbohydrates and fats and proteins that we're going to break down so that we can use that energy and turn that energy into kinetic energy, right? So that we can do work for our bodies. So again, that's important to understand that chemical energy. And of course, in 202, we're going to talk a lot about how that process happens in terms of digestion. Electrical energy. This is going to result from the movement of charged particles. And you may say, well, why is electrical energy important for me to understand? And we're going to talk a lot about electrical energy when we talk about nerve conduction, okay? So it's going to be really important for you to understand that electrical energy, and we're going to talk a lot about those movement of charged particles across the cell membrane when you get to the nervous system. Mechanical energy is energy that's directly involved in moving matter. So we're going to talk about this in terms of like mechanically gated channels and things like that. And then we're also going to, so you can like physically move some of these ion gated channels when like you push on your skin and things like that. And so that's mechanical energy. And then we're also going to talk about, again, that mechanical energy being things like muscle contraction, where you're actually, again, moving, you're using your muscles to actually move two bones in relation to each other. And then the last one here is radiant or electromagnetic energy. This is the energy that travels in waves. So things like heat, visible light, ultraviolet light, X-rays. And again, you may say, well, why are we going to talk about that in human anatomy and physiology? But think about the fact that when we get to the special senses and we talk about the eyes, right? The eyes are taking in light in this form of visible light, right? And that's what's being taken in to stimulate those receptors and form these images, these visual images that we see. So we're going to talk a lot about that, especially the visible light spectrum, when we get into the special senses and talk about the eye. So that's why you have to know those different forms of energy. Hopefully that helps you in terms of why you need to know those. And then, of course, we're going to talk about energy conversions. So remember that energy may be converted from one form to another. So again, a simple example would be like turning on a lamp converts electrical energy to light energy. For us, again, we can talk about this in terms of, converting the chemical energy, in bonds and the food that you eat into, again, this mechanical energy to be able to use that energy to do muscle contraction, okay? So those are the types of energy conversions that we're going to talk about in the human body. Now, energy conversion is inefficient oftentimes. So you know that some of the energy is lost as heat, right? If you think about it, your car, the majority of your engine is actually designed to deal with the fact that there's a lot of energy lost as heat. And so most of your car engine is to cool your engine, keep your engine cool because so much energy is lost as heat. Now, in the human body, this actually kind of ends up being some usable energy. Here we talk about, heat's lost and it's partly kind of this unusable energy. But in the human body, it ends up being kind of beneficial because as we do muscle contraction, okay, and we're, again, doing some actual mechanical energy, some of that energy is going to be lost as heat. And we're going to use that heat to help, again, maintain homeostasis in our internal body temperatures. So kind of interesting when you talk about, again, that in most systems, physical systems out there, if you're talking about mechanical systems, losing energy as heat is kind of a bummer. But in the human body, it actually is really beneficial because it helps to keep us warm. This is why when you shiver and you do muscle contraction again, when you're shivering, that you're going to release heat as a byproduct of that inefficiency. And that helps to warm the human body. So kind of interesting. We're going to talk a little bit about kind of the nitty-gritties of chemistry. So now we're going to get into what's an element, how can we put these elements together to form molecules and compounds, and then what types of molecules and compounds are important for the human body and what types of reactions are important for the human body. So obviously all matter is composed of these elements. You've seen them on the periodic chart of our periodic table of elements. These elements are substances that cannot be broken down into simpler substances by ordinary chemical means, okay? Again, by ordinary chemical means or chemical methods. So for us, the four main elements that we're going to spend the most time with are going to be the ones that make up 96% of the human body. That's going to be carbon, oxygen, hydrogen, and nitrogen. Or for most students, it's a little bit easier to remember them in this pattern, honk, because that's what I used to teach in BIO201. Hopefully some of you have already had that. So again, it's hydrogen, oxygen, nitrogen, carbon is kind of our trick, our mnemonic for helping you to remember that. Okay, so if you remember honk, then you can remember those four major elements that make up 96% of the body. So as you can imagine, hint, hint, it's probably going to be something that's important, probably going to be something that's on your test because they're the four elements that make up 96% of your body. A lot, right? Now, there are lesser elements that make up about 3.9% of the body, and these things are calcium, phosphorus, potassium. As you can probably guess, these are fairly important. So even though these elements are in a lesser amount in the human body, they're still important. We need iron to be able to carry oxygen in our red blood cells, right? We need calcium to do muscle contraction. So without calcium, we don't do muscle contraction. So again, these are really important. Without sodium and potassium, we don't do nerve conduction. So just because these elements are in a lesser amount doesn't mean they aren't important, and we will talk about them, okay? When we say trace elements are these 11 elements that make up less than 0.01% of the body, but they're usually required for enzymatic function, okay? So they're usually required to activate enzymes. So that's why when we talk about some of these trace elements, they end up being important for activation of enzymes, okay? But you don't have to know all 11 trace elements, again, because we're not even going to get into all of them in human anatomy and physiology. So we'll talk about them. I just want you to know that just because they're trace elements doesn't mean that they're not important for the human body, okay? So again, here's some examples of those trace elements, things like chromium, cobalt, copper, fluorine, manganese. Again, these, you don't have to know them. I just want you to know that trace elements are important because they're oftentimes going to be important for activating enzymes. That's all I want you to know there. All elements are going to be made up of atoms, okay? Which is our kind of building blocks for each element, okay? And so these atoms that have the same particular properties are, again, going to make up an element. So an element is kind of defined by these particular physical and chemical properties that it has. And we're going to talk about this in terms of some of those subatomic particles that are within them, things like protons and neutrons and electrons, okay? So let's go ahead and dive in. The atomic symbol is a 1 or 2 letter chemical shorthand for each element. So again, things like O for oxygen, C for carbon, you're probably already pretty familiar with this. Some of these symbols that we're going to use, you're going to get really familiar with the symbol Na which means sodium. But you may go, well, why did they give sodium? Why didn't they name it SO? And the reason it came from its Latin name, natrium. So same with potassium. You're like, why didn't they name it PO instead it's K, right? And that's because it came from its Latin name, kalium. So some of those, you'll just get familiar with these symbols as we go throughout the semester, because we're going to actually use them when we talk about, sodium and potassium and creating this membrane potential when we get to the nervous system, things like that. So you'll get really familiar with these symbols as we go along. So here's your periodic table of elements. Again, you don't have to memorize all these symbols, of course, because we're going to actually go over the ones that you need to go over in each physiological, activity that we talk about. But so you do have to understand the really basic atomic structure. And that is that we have a nucleus inside the atom, right? That is full of neutrons and protons. Neutrons, again, have no charge. They're neutral, right? And hopefully this is just a review, so I'm going to go through this quickly. They have one atomic mass unit. And then protons are also in that nucleus of an atom. And so and when I say the nucleus of an atom, right, it's going to be the center of the atom, right? And so protons and neutrons are shoved in that nucleus, and protons are easy because protons, positive charge, okay? So, and they also have a mass unit of 1. So when we talk about the overall mass of an atom, we're pretty much taking into account the neutrons and the protons, okay? Electrons, not so much, because they're really, really tiny in comparison to protons and neutrons, and they simply are just so tiny that they don't really have an overall effect on the weight, not that we measure. So we give them a 0 atomic mass unit. So when we're measuring the mass, we're really considering the neutrons and the protons, okay? So again, remember, neutrons are neutrally charged, protons positive charge, electrons electrons are electrically negative. Well, that doesn't really work for you. But if you know that P is for positive, N is for neutral, you can think of E as electrically negative. If that works for you, I don't know. Or you can just remember that it's negative because, it's not a proton or a neutron. So, and remember again that when you look at an atom, again, the protons and neutrons are going to be in that central area in the nucleus, and then the electrons are going to be in this electron cloud. So the electrons are really kind of orbiting around the nucleus, okay? And so you'll have the planetary model, which is mostly what we're going to use because we like to draw in the actual electrons, but the orbital model is kind of a more accurate model because our electrons are not just staying put right here and here, right? If you could picture them three-dimensionally, they're orbiting, all around in that electron cloud here. So again, even though the orbital model is really more correct, we're going to use the planetary model just for learning purposes, okay? Now, if atoms are electrically neutral, then obviously you have a balance of positive and negative charges, which means you have the same number of positive protons as you do negative electrons, okay? Now, different elements are going to contain different numbers of subatomic particles, okay? And that's what that's what makes the element different. And primarily what makes one element different from another element, as you're going to find, is its number of protons. Okay, so what makes hydrogen is that it has 1 proton. Now, if you put another proton into that nucleus, it's now helium. So what makes helium is that it has 2 protons. And what makes lithium is that it has 3 protons. Okay, so the number of protons inside that atom's nucleus is what defines each element. Now, hydrogen can have 0 neutrons. It can have 1 neutron. So you're going to see the number of neutrons can actually change. And we'll talk about that in the form of isotopes. Also, okay, hydrogen typically has 1 electron. But Hydrogen can also be an ion, if you've ever seen it written H+, right, to show that something's slightly acidic. So if something has hydrogen ions in it, it's acidic. And so that H+ means that it has one proton and no electrons, okay? And so it has that extra positive charge because it has no electrons. So the important thing to remember here is that the number of neutrons can change and the number of electrons can change. But the number of protons cannot change for an element. If the number of protons do change, then that element becomes another element, okay? So again, we're going to talk about these in a little bit more detail here. Things like atomic number, mass number, isotopes, and atomic weight coming up here. So again, this is just showing you hydrogen with one proton, helium, here in the center here, hydrogen with one proton, helium with 2 protons, and then lithium with 3 protons. And then here you can see they've drawn the electrons here. So this hydrogen is electrically neutral because it's got 1 proton, 1 electron. This helium here is neutral. It has 2 protons and 2 negatively charged electrons. And then this lithium here is also neutral, 3 protons, 3 electrons. Again, you're going to see that they have a different number of neutrons here, and that is going to depend on what type of isotope you are looking at for each of those elements on how many neutrons. So the number of neutrons will vary for an element depending on what isotope you have. So I'm going to get to that in just a minute. So really quick, again, identifying elements. What identifies an element as a certain element is its number of protons. So that number is so important that we call it the atomic number. It literally tells us what element that atom is. So we give it, it's a very special number, it's the atomic number. So the atomic number and the number of protons are synonymous. They're the exact same thing, okay? So for example, and we usually write this as a subscript to the left of the atomic symbol. So here you can see that lithium has 3 protons. That's its atomic number, 3. Here helium has 2 protons because that's its atomic number here, okay? Now the mass number is typically written as a superscript, as you see here. And so the mass number is going to be the total number of protons and neutrons in the nucleus. Again, why not electrons? Remember that, again, the mass of electrons is so minute, it's so tiny that we don't consider it in the overall mass because it just doesn't make enough of a difference. So again, we consider the mass number to be the protons and the neutrons. So here you can see in this example here, the atomic number is 2, which means helium has 2 protons. Its mass number is 4, which means that because it has 2 protons, that it then has 2 neutrons to give it an overall mass number of 4. Okay. So isotopes. Again, isotopes are going to be atoms of the same element that have the same number of protons but differ in their number of neutrons. Okay, so if you look at carbon here, you have carbon 12, carbon 13, and carbon 14. They're all still carbon because they all have 6 protons. But you can see that they all have different numbers of neutrons that define each isotope. So carbon 12 has 6 neutrons. Carbon 13, and we put 13 being that it's its mass number, right? So we use that to help identify what isotope it is. So carbon 13 with a mass of 13 has 7 neutrons. Carbon 14 with a mass of 14 has 8 neutrons, okay? So that's what an isotope is, just a different number of neutrons, okay? And then again, the atomic weight, when we talk about an actual atomic weight, which is, again, what we put in the periodic table of elements, that's just an average of the mass numbers of all of the isotope forms of an atom that exists naturally. So what we do is we say, okay, we're going to just take the average of like the carbon 12, 13, and 14 that's out there and the percentages that they're out there, and then calculate what the average mass number is of all of those. So that's why you may say, well, why is the mass number usually like a decimal point? And that's because they're just taking the average of these different isotopes that occur instead of just, you know, measuring only carbon 12 or only carbon 13. Okay. So here, this is just showing you the different isotopes of hydrogen. So again, hydrogen can have, and when we typically say hydrogen, we're typically talking about the form of hydrogen where there are 0 neutrons. And then there's deuterium, which actually has one neutron, and then we have tritium, which actually has 2 neutrons. So you can see again, atomic mass here is 1, 2, and 3 here respectively. Okay. Now, why is it important to understand isotopes? And why do we care about isotopes? And one of the reasons is that we use radioisotopes for, medical purposes. So radioisotopes are just isotopes that decompose to more stable forms. And as they do that, they actually lose some subatomic particles. And those subatomic particles can be picked up on as they're losing those subatomic particles. They can actually be picked up on scans. And so this is nice and important tool for us. So again, sometimes the loss results in an isotope becoming a different element over a long period of time if it actually loses a proton eventually. And that's what we call decay. As isotopes decay, again, subatomic particles that are being given off release a little bit of energy, and that energy is referred to as radioactivity, and that's what we detect on our scanners when we use radioactive isotopes. And of course, I have to give credit to Marie Curie, who actually discovered radioactivity. She was pretty amazing scientist. If you haven't read about her, please take some time to read about her. So radioactive isotopes today, again, are important because we use them as biological spies, if you want to call them, in medicine. So what we can do is living cells don't actually know the difference between the normal non-radioactive isotope of that element that they use. So if an organ uses a specific non-radioactive element, if we inject the radioactive element, the organ and the living cells don't know the difference, and they'll take up that radioactive element. And then as that element is being taken up, it's going to release some of that energy because it's radioactive. It's releasing some of those subatomic particles, and then we can pick that up on our scans. So this can become really beneficial in, certain diseases. These are actually picking up, these are scans looking for brain tumors. And so we use, again, these radioactive isotopes because your cells don't know the difference, okay? And so oftentimes what happens is when you have cancer, usually those cells will bring in more blood flow to that area. And so they'll take up these elements faster than the surrounding tissue. And so they'll usually light up. So oftentimes that's why tumors will light up on scans. So just kind of interesting information on why radioactivity is important. Now, all radioactivity, if we talk about especially in higher doses, can actually do quite a bit of damage to living tissue. So, and we know this because radioactivity, can cause cancers. So, when you talk about things like Chernobyl, where there was a release of a large amount of radioactivity, there was an excessive exposure to radioactivity, and that ends up actually damaging the cellular molecules and especially the DNA inside your cells. And that's when we see things like cancer show up. Okay, so we're moving right along here to molecules and compounds. So, and again, I know I'm going through this fast because this is just kind of a review here. So keep in mind that when we combined atoms together, we can form molecules and compounds. Now, a molecule is just simply a special term that we give to two or more atoms that are bonded together. So again, for example, if you put together one oxygen atom with another oxygen atom, then we make O2, or an oxygen molecule, okay? Now, to make a compound, that's just if we do two or more different kinds of atoms bonded together. So again, molecules are going to be when we just put, again, one type of atom together with again, its same type of atom. That's going to be something like H2 or O2. That's a molecule. Where when we put two or more different kinds of atoms together, that's when we're making a compound. So things like glucose, C6H12O6. That's going to be a compound, okay? Again, just a bit of terminology because we're going to use those terms, molecules and compounds. Now, most matter is going to exist as a mixture, right? Two or more components that are kind of physically intermixed together. So we need to talk really quickly about what solutions, colloids are, and suspensions. And this is just my funny meme for you. So when we talk about a solution is just, and this is where we're going to talk mostly about solutions, because again, we're going to be talking about a lot about what happens on one side of the plasma membrane versus the other side of the plasma membrane. So in a solution, again, we have our solute particles that are going to be really tiny, and they're going to be typically dissolved in some type of liquid solvent, okay? And that's what makes up our solution. And again, oftentimes, again, the solute won't settle out when it's in solution or scatter light. So that's one of the ways that you know you have a solution. Now, a colloid is going to be where you have solute particles that are larger than in a solution, and they are going to scatter light. So they're not, but they're still not going to settle out, okay? So when you think of something like Jell-O, okay, this would be a good example. A lot of gelatinous substances are going to be colloids, okay? And then suspension is where you have these solute particles that are really large in that they do settle out. So you can temporarily kind of suspend them, but if you leave them sit, with gravity, they'll settle out. So things like blood. You know, if you were to take your blood and leave it out and leave it set out for a long period of time, the red blood cells are more dense and they'll actually settle down to the bottom, okay? Okay, so again, this is just kind of the version, the wordy version here, talking about colloids again, or these emulsions. But again, the big thing is you have larger solute particles here in solution, but they don't settle out. And so sometimes they'll give it a cloudy or milky look. Also, again, gelatinous. So when we talk about a lot of the gelatinous fluids in the body, so when we're going to talk about things like serous fluids, they're going to be these colloids, okay? So, and then again, solutions, when we talk about solutions, you do need to know these two terms, solvent and solute. So solutions are going to be, again, these homogeneous mixtures, meaning the particles are kind of evenly distributed throughout. Again, that those solutes are not going to settle out. The solvent is typically, again, the substance that's present in the greatest amount, and it's usually liquid, and in the human body, it's almost always water, okay? The solute is going to be the substance that's dissolved in the solvent, so dissolved in water. And again, it's usually present in smaller amounts. So example, you know, blood sugar. So glucose is the solute and the blood plasma is the solvent, okay? So most solutions in the body, again, are true solutions of either gases, again, liquids, or solids that are dissolved in water in the human body. Now, the concentration of true solutions. So there are kind of three common ways to express concentrations. Sometimes we express it as a percent of the solute in the solution. So how many parts solute are there in 100 parts of the solution? And again, the solvent is usually water. So for example, if we're talking about like the salinity, we might say how many parts salt to how many parts water. So a 10% salt solution would mean 10 parts salt to 90 parts water, okay? We can also do some solutions in milligrams per deciliter. So you'll see glucose is actually measured this way. So again, a deciliter, just as a reminder, it equals 1/100th of a liter. I'm not going to test you on this, but I just want you to know what this means when we say milligrams per deciliter, because that's how you're going to see blood glucose displayed, okay? So for example, again, normal fasting blood glucose levels are going to be around 80 milligrams per deciliter. So again, 80 milligrams of that glucose per deciliter of, you know, plasma, okay? And then molarity is the last kind of term that we're going to use, and that's just the number of moles of solute per liter of solution. So again, I used to, when I was in high school, they'd sing the song, molarity, molarity, it's moles per liter of solution. You take the grams, convert to moles, and divide by liters of solution. that helps you remember molarity, then there you go. There's my high school song. Believe it or not, my high school teacher made us sing this over and over again. And of course, me being a teenager would just roll my eyes. And then here I am, 30 years later, I still remember his molarity song. So anyway, you never know what little songs are going to stick in your head and help you out later on. But again, that's what molarity is. And so we use what a mole is. You might go, what's a mole? Not this mole, but like a mole of a compound is equal to its molecular weight in grams. And so when we talk about something like glucose has a molecular weight of 180.12 atomic mass units. So 180.12 grams is a mole of glucose. Okay. And so again, if you add enough water to make 1 liter, then you have a 1 molar solution of glucose. So a 1 molar solution of glucose is 180.12 grams of glucose in a liter of water. Okay. Again, I'm not necessarily going to test you on, molarity and have you calculate molarities, but I like you to know just what the term is, because we're going to use the term molar solutions when we talk about different, again, substances in the body. So just kind of a good idea and to know that. And again, a mole of any substance is always going to be, it's going to contain 6.02 times 10 to the 23rd molecules. That's Avogadro's number. Do you need to know that? No. I really want you to kind of more understand just what molarity is, especially in terms of like this example here, so that it just kind of makes sense to you on what we're talking about when we talk about molar substances, okay? So again, molarities in the body are typically so small that they're expressed in millimoles. So again, 1,000 millimoles equals 1 mole, okay? But when we're talking about these substances in the body, again, 1 mole is of that substance is too big, and in the body we're talking about things that are smaller. Okay, so we'll use millimoles, 1/1000th of a mole. Okay, so hopefully that makes sense. Again, I'm not going to spend too much time on this. I just want you to be aware of what it is. I'm not really going to test you on molarity per se, but I just want you to know what it is so that when we talk about millimoles, you know what that is. The difference between mixtures and compounds. So again, unlike compounds, mixtures don't involve chemical bonding between any components. Mixtures can be separated, even if it has to be by physical means. We can separate them, like such as straining or filtering. For example, salt water, right? Salt water is a mixture to solution, but obviously if we left that salt water out on the counter long enough, the water could evaporate off, and then we would separate out the water, and then the salt would be left behind, okay? So that's the difference, again, between salt water being a mixture versus a compound being something like carbon dioxide, okay, or the glucose itself, okay? So glucose itself is not going to be broken down by normal, again, chemical means. So again, unlike compounds, mixtures do not involve chemical bonding between components, and they can be separated by physical means. Compounds can be separated only by breaking those chemical bonds, okay? And we'll talk about that, how that happens in terms of things like digestion. Mixtures can be heterogeneous or homogeneous. Again, it just depends on that type of mixture and what it is, on whether or not that mixture is homogeneous and they're, all those solutes are mixed throughout, or whether or not they're heterogeneous and they end up being something like your blood that can settle out. And then compounds, again, are only homogeneous, obviously. Again, a little more detailed than we're going to get into. So let's talk a little bit about chemical bonds, okay? And this energy in the form of these bonds between these actual chemicals here. So as you probably remember, chemical bonds are energy relationships. It's not an actual physical structure, okay? So what that means is, you probably remember, chemical bonds are all about electrons, either the sharing of electrons or the transfer of electrons, okay? And that energy relationship between the two because of their electrons. So electrons are really going to determine going to determine the chemical bonds that we're going to see, okay? So, and even again, the chemical reactions that take place. So let's get into, again, some of just the review on this. So remember that electrons can occupy areas around the nucleus and then what we call the electron shell. And there are different energy levels that the electrons can inhabit around in that orbit. And depending on its size, an atom can have up to 7 electron shells. Now, we're not going to really go beyond talking about the first and the second shell too much, because what we really want to focus on is that first shell can hold 2 electrons, and then that next shell, and then each shell after likes to fill it in kind of these shells of 8, okay? So what that means is, like, shell 1 here can hold only 2 electrons. Shell 2 is going to hold a maximum of 8 electrons. So after shell 1, really our atoms that we're going to talk about are going to want to have an outer shell of 8 electrons to be full, okay? So other than talking about hydrogen and helium, so again, hydrogen here, to have its kind of full electron shell, it to be stable, it's going to want to be here in terms of electrons. So it will want to interact in ways in which it can become more stable and fulfill its outer electron shell. So if you look, all of these elements here, these are called the noble gases. And they're kind of high and mighty noble because their electron shells are full. And so here, if you look, this electron is the first electron shell. It has, again, 2 electrons that fill its shell. And then it's stable, right? Here in this level, there are 8 electrons. And so neon has 8 electrons in its outer shell. So it's stable. And what that means is these noble gases have the atoms have these full outer electron shells, what we call the valence shells, and they don't really need to interact, which is why they don't like to interact. Helium's very stable because it doesn't really need to interact with anything else to fill its electron shell. It's already full. Same with neon, same with argon. It already has that full electron shell, okay? So the things that are in this, the elements that are in this column are the noble gases. They're high and mighty. They don't need to interact with anything else, okay? They're really stable. Now, everything else here, so we talk about carbon, nitrogen, oxygen, even fluorine, they're going to want to interact with other atoms of different elements, or even atoms of the same element, in a way that they can fill that outer shell, okay, of electrons. So the outermost electron shell is our most important one in terms of bonding. We call it the valence shell. And the electrons in the valence shell have the most potential energy because they're kind of the farthest away from the nucleus. And those are the ones that are involved with chemical reactions. Those are the ones that are going to determine how things want to bond with other things. So again, we have this octet rule, the rule of 8, where atoms desire to have 8 electrons in their valence shell, other than, again, those smaller atoms, hydrogen, helium, because they only have the first shell, which is full with 2, okay? But everything else wants to have 8 electrons, especially everything else that we're going to talk about in the human body, wants to have 8 electrons in its outer shell. It's going to interact with other atoms of either the same element or different elements in a way in which they can fill that valence shell. So it's all about having 8, okay, in that outer shell. So again, most atoms don't have full valence shells, and they want to either gain or lose or share electrons in a way that fills that outer shell, okay? So we already talked about helium and neon. They already have full shells, 2 here in that first one, 8 in that second one for neon. So their outermost valence shell is full. They're chemically inert. They don't like to interact with anything else. Now, these guys are the reactive elements because, again, their outer shell isn't full. So here, hydrogen, again, only has 1 electron, but it likes to have 2 electrons, okay? So hydrogen oftentimes likes to bond with another hydrogen. They'll each share an electron with each other so that they can have that full valence shell, okay? Or again, carbon will often do that as well so that it can share its 4 electrons and then get another 4 electrons shared with it from something else so that it can fill that outer shell and have 8 electrons, okay? And then here, when you look at something like sodium, right? Sodium in its outer shell, it only has 1 electron in its outer shell. So how many electrons does it need to take on in that valence shell to be happy, to be stable? It wants to take on 7 electrons. That's a lot of electrons, right? To share its electron with something else that's going to share 7 electrons with it. So that's kind of a lot. So sodium doesn't really like to form covalent bonds, which we'll talk about in just a minute, which is sharing. It really just likes to give up that outer electron and form what's called an ion. Because again, if it gives up that 1 electron, then look, that shell right below it is full. So then its valence shell becomes this shell, the second one here, and it's full, okay? So let's talk about this in the types of chemical bonds. We have ionic bonds, we have covalent bonds, and we have hydrogen bonds, okay? And so here, this whole example here will kind of make sense in just a minute here. So again, these different types of bonds are going to depend upon how these atoms are going to interact to fill that valence shell. Now in ionic bonds, just like we talked about there with sodium, and then we'll talk about it with chlorine as well, these are going to be atoms that are going to gain or lose an electron to become charged. So usually these are going to be atoms that maybe just need 1 electron to come over to fill their valence shell, or maybe even just 2, or they need to give up 1 or 2 electrons to fill their outer valence shell, okay? So again, here we're going to form, typically in this case, what we call ions, because you're going to be talking about gaining or losing an electron. Now, if something loses an electron, right? If it gives up an electron, now, first, let's talk about it. First, if it was neutral, it has the same number of protons as it does neutrons. Okay, positive and negative charge are equal. But if it has to give up an electron, right? Now it's going to have an extra proton, so an extra positive charge. So it's going to become what we call a cation, okay, to be positively charged. Now, if that neutral atom instead, a different one, okay, something like chlorine, needs to give up that electron, okay, to form a full outer shell, it needs to gain, an electron to fill its outer shell. So again, that's something like chlorine. And it's going to take on an extra electron. Now it's going to have an extra negative charge, and it's going to form an anion, okay? So again, an example of this would be sodium forms a cation because just like we talked about here, okay, it wants to give up that electron right here. Now, on the reverse side, something like chlorine, okay, it has 7 electrons in its outer shell. All it needs is 1 more. So it will take that extra electron, usually from something like sodium that gave it up, and it'll be like, hey, I actually need that extra electron. It'll take it on, and then it ends up with this negative charge, right? Because it has 1 extra electron now, okay? So ionic bonds involve the transfer of valence shell electrons from one atom to another, and this results in ions. So if one again becomes an anion, meaning that it gains an electron or more than 1 electron, then it becomes negatively charged, okay? So something like chlorine, when it takes on that extra electron, it becomes negatively charged, and we call it an anion. So that is a term I want you to know. And to help you remember, this might not work for you, but I'm not a big fan of onions. I'm sure a lot of people really like onions, but I'm not a super big fan of onions. And so they're kind of like a negative thing to me, or, onions smell kind of. So anyway, you can think of that as negative and anion, onion. They're kind of close together, just a switch of a vowel. So that's my trick for you. If that works, it might not work, and you might have to come up with your own trick there. And then cation is for positively charged particles, and so, or positively charged atoms. And so again, something like sodium, right? When sodium gives up its extra electron, then it ends up having an extra positive charge. And so it becomes positively charged. We call it a cation. So again, I think of cats as positive. They're cute, positive. So cation has a positive charge, if that helps you remember cation and anion. So again, anion is something that has a negative charge, and cation is an element that has a positive charge. And of course, opposites attract. So that's what forms your ionic bond, is, between something like sodium, which is a cation, and chlorine, which is an anion. Those opposites attract, and that attraction is what forms your ionic bond between sodium chloride, and that's exactly what they show here. So again, here you can see that sodium, really quickly, I'll just kind of go through this. Sodium has that one electron in its valence shell. Dude, it wants to give that electron up so that that second shell can be full, okay? So it is happy to give that up. Now, it bumps into chlorine here. Chlorine's like, whoa, dude, I have 7 electrons on my outer shell. I only need 1 more. Like, we're a perfect match. So sodium gives up its electron here. Now it becomes a cation, right? Because it has given up that electron, and now it has an extra positive charge here as soon as it gets that up, right? And so it becomes a cation. And then chlorine is like, dude, give me that electron. I want it. Now I have a full outer valence shell. And when it takes on that extra electron here, now it'll have an extra electron, because it'll have 18 electrons instead of 17. And so it's going to have an extra negative charge. So it becomes an anion. Okay. So now here we have sodium. That's now a cation. Chlorine, that's an anion, and the opposites attract, and that attraction is what forms our ionic bond. So our ionic bond here is just the attraction between the positive and negative charge, okay? So it's not a super strong bond. And you can see there are going to be trends for, again, things that, obviously things that are in this column are going to want to, give up that extra electron, because then, the valence shell below it will be full. Even things in this column, they just have to give up 2, right? So even like magnesium likes to become a cation, because it's happy to give up those 2 electrons to have a full outer shell. And then things that are in these columns, especially obviously this column here, like to take on electrons, right? So it only needs 1 electron here to fill its outer shell, 2 electrons here to fill its outer shell. So these things are more likely to become anions, okay? So more likely to become cations, more likely to become anions. And again, I'm not going to give you a periodic chart. I just want you to understand that, so that you understand what ions are. Because we are going to talk a lot about ions, especially when we get into nerve conduction, when we talk about muscle contraction, we will talk a lot about ions. Most ionic compounds are salts. So when they form those ionic bonds, they form salts. And when dry, the salts can form crystals inside of these individual molecules. So for example, that's an example of sodium chloride. So again, here now you take that sodium chloride and you mix it in water and really stir it up. And what ends up happening is you can separate, again, these ions, and they'll actually interact with the water molecules instead. So you can, again, ionic bonds can be broken. They're not your strongest form of bond. And covalent bonds are based on sharing of electrons. So covalent bonds form when you share 2 or more valence electrons, okay? And so you can share 2 electrons, which forms a single bond. Each one, again, is going to share 1 electron with each other. Here, in this case, an oxygen, each of these oxygens are going to share 2 electrons with each other. And so that's going to form a double bond. And then if you had one that was sharing 3, it would form a triple bond. Okay? So again, hopefully all terminology that you kind of remember. Now remember that there are different types of covalent bonds. So not all sharing is equal. So sometimes you have these polar covalent bonds where the sharing is not equal, and sometimes you have non-polar covalent bonds where the sharing is equal. Okay, So let's just talk a little bit about this. Here you can see each of these hydrogen atoms. They have 1 electron in their outer shell. They want to have 2, remember? So they're going to, again, come into contact with carbon, who has 4 electrons in its outer shell. It wants to take on 4 more to have 8, right? So what it's going to do, and remember, hydrogen here only wants 2 because it's just its first, it's on its first shell. So what's going to happen is the carbon and hydrogen get together and they're like, hey, look, I'm going to share 1 with you, you share 1 with me, okay? And if carbon does this with 4 hydrogens, then it's happy because now it can count those electrons that it's sharing. So here, 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer shell, right? And each of these hydrogens is happy because, look, here we go, 1, 2, right? And it's got its full outer shell now. So again, this is what our covalent bonds are. So when we talk about these molecules and compounds, especially that are covalently bonded, these are stronger bonds, okay? Because they're not just based on attraction, they're based on actual sharing of electrons, okay? So here's something like oxygen. If you put 2 oxygen atoms together, they're going to each pull equally on those shared electrons. And in this case, again, these oxygen, if you look here, we have 1, 2, 3, 4, 5, 6. This one has 6 in its outer shell. So each one wants to take on 2 more. So each of them just this guy says, hey, I'll share 2 with you. You share 2 with me. We'll each have full outer shells now, and everybody's happy, okay? And they actually will share equally because oxygen is paired up with another oxygen. Here, this is a triple bond, okay? Because they each want to share, they each want to take on 3, so they each share 3 with each other. So that was just showing you a double bond here, okay? With 4 electrons and a triple bond. Now, let's talk more importantly about what non-polar versus polar covalent bonds are, because those are going to be important for you to understand. So non-polar covalent bonds are where we have equal sharing of the electrons, okay? So this results in kind of an electrically balanced molecule. They're equally sharing the electrons here. Each electron is spending an equal amount of time with this, in this case, this hydrogen and this hydrogen, okay? So there's no bully pulling the electrons closer to them, and the electrons are not spending more time with one atom versus another, okay? They're completely equally shared, and that's what nonpolar is, okay? So carbon dioxide is a perfect example of this, okay? Now, polar covalent bonds are when there's unequal sharing of electrons between 2 atoms. And this is going to result in kind of polar molecules where you're going to have kind of a slightly negative charge on one side and a slightly positive charge on the other side. And that's because what happens in this case is that you have, you know, one of the atoms in the relationship being a bully, okay? So one atom has a greater electron attracting ability. We call that electronegative than the other one, okay? And so in this case, the chlorine here is the bully, okay? In the sharing of electrons. And it's going to pull those electrons closer to it. So the electrons are going to spend more time around the chlorine than they are around the hydrogen. They're still sharing. It's just unequal. And so that's going to leave the chlorine with a slight partial negative. It's not taking that electron, so it's not a full negative, still sharing it, but it leaves it with a partial negative. And we actually draw that with this little delta. Oh, here we go. This little delta symbol right here, okay? To show kind of a partial negative charge. Oh, here you see that right here, okay? And then the other one here, the hydrogen, now the electrons are not spending as much time with it, including its own electron. So it's going to leave it with a slight positive charge, okay? So this becomes really important in polar covalent bonds, okay? I'm sorry, in water molecules as a polar molecule. And really quickly, I'm just going to turn on my video here. So again, when we talk about water molecules, oxygen is going to be your big bully atom here. And what it's going to do is, if this is oxygen, okay, and it's sharing its electron with hydrogen here, that's sharing its electron, okay, what oxygen is going to do is it's going to pull the electron closer to that oxygen, okay? So again, this oxygen is the bully, and it's going to take those shared electrons and pull it closer to the oxygen over here, so that those electrons spend more time with the oxygen and less time with the hydrogen. And so that's what a polar covalent bond is. You have to have a bully. So I always like to take two students, and I have their hands represent the electrons, and they have them grab hands to form that covalent bond where they're sharing. And then what happens is, when I want to show that it's a polar covalent bond where there's unequal, I have one be the bully and pull the electron closer to it. Now they're still shared, right? But it's just that the electrons are spending more time with one versus the other, okay? And that's exactly what happens in this polar covalent bond. Here again, you have in a water molecule, remember, you're going to have an oxygen. An oxygen, being that it has 6 electrons in its outer shell, wants 2 more to fill it. Each hydrogen has 1, and it wants 1 more to fill it. So oxygen says, hey, I'll share 1 with you. You share 1 with me. And then it says the same thing to this hydrogen over here. But the thing is that oxygen is a little bit of a bully, and oxygen is going to pull those electrons closer to it, okay? And the electrons are going to spend more time with oxygen, and it's going to give that oxygen a slight partial negative charge. Now, the hydrogens are going to have a slight positive charge. And what this does is this makes water molecules polar, okay? So now they're going to have a negative, partial negative on this end, and a partial positive on this other end. And that is going to determine why water molecules like to interact with other water molecules and other charged particles themselves, okay? So again, this is just talking about the difference between ionic bonds. It's just kind of reviewing the difference between ionic bonds, which is transfer of electrons, covalent bonds, which is sharing, polar covalent unequal sharing, and non-polar covalent equal sharing. So it's kind of a good review of everything. Now, hydrogen bonds are going to be formed due to the fact that those water molecules are polar molecules, okay? And so hydrogen bonds are going to be formed based on the attractive forces of these partial positive and partial negatives, okay? So this happens, again, mostly with water molecules. So when we look at something like a hydrogen bond, again, this is not going to be as strong as a full ionic bond, because an ionic bond is a bond between a full positive and a full negative charge, right? This is going to be a bond between a partial positive and a partial negative. So for example, okay, when you put water molecules together, again, if you look at your glass of water, your water molecules are actually forming hydrogen bonds with each other. So what's happening is the partial positive charge on the hydrogen end of the water molecule, of one water molecule, is actually forming a temporary attraction with that partial negative charge on the oxygen, okay, of another water molecule. And so that's what kind of holds water together. Like if you pour water out, even the liquid water on your desk, the water kind of stays together. And the reason that it stays together and the water molecules just don't scatter all over your desk, right, is because of these hydrogen bonds that, again, like to keep the water molecules together. Now, what's interesting is when you look at your water in the liquid form at room temperature, what ends up happening is these hydrogen bonds are, again, kind of temporary bonds. And so they're easily broken. And as these water molecules are moving in a liquid form, then they're constantly kind of bumping into each other and like making new bonds with each other and like breaking bonds and making new ones with each other. So, they're kind of very flirtatious molecules. They'll quickly form a bond with this water molecule, and then another one bumps into it and they'll form a bond with that one and break the bond with the other one. So again, these hydrogen bonds are, again, these very kind of temporary bonds, okay? Now, altogether, the hydrogen bonds can be quite strong. So the combined strength of all of those water molecules can actually be fairly strong. And it's what actually creates our surface tension. So you felt this if you've ever done a belly flop on the water. You're like, whoa, dude, all those hydrogen bonds together, are really strong. If you just push your finger into the water, that's not so bad, right? Because you're not breaking as many hydrogen bonds. But if you're like doing a full belly flap, that's a lot of hydrogen bonds, and you feel it, right? So again, a water strider can walk on a pond because of that high surface tension of the water that results from the combined strength of lots of hydrogen bonds. Okay. So let's see. I know this has run a little longer. I like my lectures to be about 40 minutes, but I'm going to go ahead and just try to get really quickly through chemical equations, and then I can go ahead and I'll stop after this. So chemical equations just occur when chemical bonds are formed, rearranged, broken, and it makes new bonds. So that's what's happening when we talk about chemical reactions. Again, when we're making chemical bonds, or we're breaking chemical bonds, or rearranging them. And we can write these, obviously, reactions out in a symbolic form to make sense for us. So typically in our chemical equation, remember, we're going to have reactants, which are the substances kind of entering the reaction. They're the beginning substances. And then the products, which are going to be the end substances, the result of that chemical reaction, the products. And the amount of reactants and products, again, can be shown in these like balanced equations that we have. So obviously, compounds, again, we can represent in these molecular formulas like H2O. You already know that means two hydrogens that are going to be covalently bonded to an oxygen. C6H12O6, again, means 6 carbons are covalently bonded to 12 hydrogens and 6 oxygens. Okay. And so those subscripts, again, indicate the number of atoms that are going to be joined by those covalent bonds. And then so here, when we put a number in front, this just means that we have 2 water molecules, okay? But here, H2O, this is showing the bonds, right? So there's 2 hydrogens bound to an oxygen, if that makes sense. So again, when we talk about these reactions, we're going to have our reactants, which again are kind of the beginning substances, and then the product, what we have at the end of that chemical reaction. So we can have these building reactions where we're putting things together, and then we also can have breakdown reactions, which isn't shown here. We just have these building reactions. Okay. So let's talk about that. When we have a building reaction where, again, we're actually putting together, 2 or more substances, atoms, molecules together to form a larger complex molecule, we call this a synthesis reaction. And this is going to be used in what we call anabolic or building processes. So synthesis reactions are going to be used in anabolic processes, or building processes. And you can think of, again, anabolic, kind of like anabolic steroids, if you want to think of that. That's a building process, okay? So our synthesis reaction is just like it sounds. You're synthesizing a substance. You're taking, atom A, putting it together with, B, and forming AB, okay? And so, for example, you might be taking amino acids and putting them together to form a protein. That's a synthesis reaction. Now, decomposition reaction is going to be just the opposite. It's going to be a breakdown reaction, the reverse of the synthesis reaction. And this is going to be involved in our catabolic or breakdown reactions. Okay, so it would be just the reverse. So maybe you take now this protein and you're going to be breaking it up into its individual amino acids, or you take up a more complex carbohydrate like glycogen and break it up into its individual glucose molecules. Okay, so that's a decomposition reaction. And then we see these decomposition reactions in our overall, what we call catabolic or breaking down processes. And then we can have an exchange reaction, which is pretty easy. It's just where literally you're kind of, you're just literally exchanging one substance for another. So, AB plus C gives you AC plus B. You just exchanged, okay, some of the atoms involved in here. So the example for this would be ATP, where it transfers its kind of terminal phosphate group to glucose to form a glucose phosphate. Again, this is just kind of, it's just kind of transferring it. It's exchanging that. In this case, it's just exchanging this over to that phosphate group over to the glucose. Okay. And then sometimes you'll have like an equal exchange back. So if you want a quick, nice review of these chemical reactions, this is a great video and it's not that long. I highly recommend you watch it. It's using the Flintstones and I think it's kind of funny. So if you want to watch that, that might really help you out. I'm going to go ahead and stop here and then I'll talk about redox reactions I'll start the next lecture with that. And then, like I said, if you have any questions, I know I went through this quickly, please feel free to contact.